Hello everybody, thanks for taking the time to come here tonight. Here are the topics that we are going to present. I'm going to start with the motivation, then we will detail the development life cycle of the deep learning project that we worked on, and then we'll have a demo at the end. This picture was from an article from the National Geographic magazine titled "The World's Biggest Lakes they are drying up." So this is once upon a time it was Bolivia's second largest lake with a surface of 3,000 square kilometers, and on recent years this lake has vanished into the air. Yes, sadly, this lake is gone. And also, these climate changes around the world, it's warming lakes faster than it's affecting the air and the oceans. On top of that, thousands of families who live near these areas, near the lakes, they don't have water to drink anymore, and they lost their jobs. So this is causing a massive migration movement into the big cities. So the question is how much these changes are taking place over time. Does the government authorities, they have tools to measure this kind of climate changes? So the purpose of our project is to study the use of deep learning with satellite images to try to estimate how much water this surface are changing over time. Here are some lakes of interest that we are going to focus because they are very sensitive to climate changes, and also because they are isolated. So it means that they are not connected to any kind of water resource, and they are the ones that are suffering the most significant changes over time. So now Karl are going to start talking about the data collection part of our project.
Hello everyone. So before I start digging into the project, I just want to prevent confusion by knowing that I started. So you might recognize from time to time some pauses in my speech. Yeah. So we collected around 1,000 images in order to create a model that predicts the surface of lakes. So the majority were coming from the SIS dataset, which is a publicly available dataset. In addition, we also collected satellite as images. As Karl mentioned, we divided our dataset into a train set, which was used to train a model, and a test set, which was used to evaluate the performance of the model. These images we detect in a unit that's deep neural network, which takes an image as an input and outputs a mask that contains labels telling you whether the respective pixel was a lake or was not a lake. The unit basically consists of two components, an encoding pass and a decoding pass. So basically, the encoding pass is a sequence of filter actions and cropping actions, so reducing the size of the image, so that as you dig deeper into the network, you can select more concrete features. which might even have a lake. So we also need to know not only if there's an image, but also where it is. So the decoding pass takes care of that, was upsampling the lakes, so that we obtain the lake ones. In order to evaluate our models, we need to have labels. So, as for the training set, we were already having all of the images. So we were using the Make Sense tool, which is an online web application in which you can manually create masks. So you might see the dots here, so you can manually draw on the map. For a test step, we used the OpenStreetMap website, where we were collecting tiles, including lakes, and extracting the longitudes as latitudes, and using this for as downloading these images from the Sentinel Hub, and again using the Make Sense tool to create the masks. So before I introduce you to our first model, I would like to introduce you to our performance metrics. We use the J-Card index and the dice coefficients. So these are basically similarity measures which gives you an idea how good our predictions match with our truth. Yeah, so this is our first model. As you can see, this is J-Card index. Already, as before, it's kind of nicely. When you see there's some kind of overfitting, so that the model that performs better on the training data than the unseen segmentation data. So we aim at increasing the sample size, which we have done by image computation. So this is like you rotate the image or you increase color intensity. By doing this, we kind of doubled the sample size, which led to a 3% increase of the J-Card index. But you still see a tendency for overfitting. And that's where Max is going to introduce you to our optimization.
Thank you, Karl. Well, for the optimization part, we have studied 8 strategies. We started with dropout and the adaptive learning rate, as well as early stopping. Then we also tried a bigger network, with more bigger filters. We studied as well the use of batch regularization. So this is what I'm going to cover on this table are the results of the 4 approaches that we studied to optimize the baseline. And these are the test results, and the results are much better. We were able to have like the J-Card index reaching a plateau around 82% of precision. So it's 82% matching the predictions against the ground truth. These 4 optimizations were using the binary cross entropy as the loss function. So as the next step, we also tried to use the dice coefficient loss as the loss function, because this metric is better to work. It's better to deal with the class imbalance for the cases where the image doesn't have too much water compared to the amount of land. So we were able to train our model for much longer, for 500 epochs, and we got very nice results. And the loss function was very low, less than 0.1. and the dice index was 92%. So these are the test results that we have using the 359 images on the test set. So this is all unseen data that the model did not see before. And as you can see, we had a very significant amount of pictures with less than 70% of accuracy on the right side of the chart, saying that the model is doing a very nice job. And of course, here I'm going to present some examples that the model failed to do a nice prediction, but as you can see, the images from the training data set, even for humans, they are not quite easy to identify the water response. Also, as a part of the optimization techniques, we studied these conditional random fields. That is a technique to improve the labeling that we made manually. So as you can see on the pictures, the contours lines on the blue ones are the ones that we made, and the red ones are the ones using conditional random fields that are based on Gaussian curves, based on the colors, and on the dispersality of the labels that we created. So at the end, to wrap it up, the optimization creates an ensemble model that is the one based on this technique, the conditional random fields. We also used the best model that we got using the dice coefficient loss, and the one that was performed better using the binary cross entropy. So for the demo that Karl is going to demonstrate, we are using 3 models to predict, and the prediction that has the better result is the one that are going to be shown on the screen. So Karl.
So this is the app that we created. There's a drop down in which you can select a lake of interest, and it includes all the lakes that as mentioned in the introduction. So once you select the lake, it collects it forms the model as 4 times for every year. So there you can see the water surface in every year. So like in 2016, 42% of the image took up the water. So in this case, you see the prediction fits quite well. It well predicts the surface of the lake. You can also select it here, or no max select in the lake. You can zoom into the map and see its geographic location. So in this case, you see there's an increase of its water surface over time. Yes. Yeah, so we see this, that's a little complicated check, but the model sort of fits well. It also matches with the increase. So here you see this water body covered by the model. So the yellow contour is the model prediction. And you see there's quite a nice this contrast between the lake and the surrounding area, so the model picks up quite good on that. This is another example. So here you see the water surface is sort of fluctuating, like in 2019. So you see the model quite well matches the surface. here in 2018, yeah, you see that there's an increase there, which might be not so accurate, just a modest pick up and some noise. And also you see that like the contrast between the lake and the surrounding region is not as good as in the previous slide, for example. Yeah. If you're interested, you can also see the surface area in square meters down there. Yeah, this, I actually pretty much like this image, so you see this reflex change rather drastic. So, okay, this picture is sort of blurry, but if you just look at the picture, it's visually, you see that the water content changes drastically. And so yeah, this happens in between 1 year. So also there's still some flaws in our model. It's able to predict drastic changes in a pretty short time. So yeah, that's basically it so far.
That's it that we have. Thank you very much.